Okay, this is the second half of 4.2, properties of rational exponents and radicals. And radicals is really what we're going to be talking about. So I thought I would throw up a picture of a bunch of radicals. Get it? This is the Clash. They are actually one of the key bands that influenced the punk genre of music. So they were radicals for their time. Okay, I know, dumb joke, whatever. Okay, so this is in your book, so you don't necessarily need to write this down, but it says an expression involving a radical, okay, this is a radical, with index n, okay, is in simplest form when these three conditions are met. Okay, now remember, simplest form doesn't mean it looks simpler. Sometimes when we put something in simplest form, it looks more complicated than what we started with. So just kind of keep that in mind. Okay, no radicands have perfect nth powers as factors other than 1. So for example, if I have the square root of 50, this is not in simplest form because I have a factor that's a perfect square in there, and it's 25. So that becomes 5 times the square root of 2. Okay, no radicands contain fractions, so I can't have the square root of 3 over 5. And that kind of, that one is easy to fix because all you do is do the square root of 3 over the square root of 5. But then that leads us to the next one, which is that you can't have a square root in the denominator. So in this case, with square roots, I would just multiply it by itself down here, and I would get the square root of 15 over 5. Okay, so let's look at some examples here. If you were in class, you got a half sheet of paper that had perfect, that had square roots and cubes and numbers to the 4th power, numbers to the 5th power, and that's really nice to have. So if you don't have that and you want it, let me know and I'll send you one if you didn't get it in class. Okay, so write the expressions in simplest form. So here I have a cube, and do I have a perfect cube factor in here? And I do. The perfect cube is 27. So 27 times 5 gives me 135. And 5 does not have a perfect cube, so that one's simplified, but this becomes 3. So this is 3 times the cube root of 5. Now over here, we have a radical in the denominator, and we can't have that. So this is kind of tricky. Remember that we're trying to get a perfect factor, not a perfect factor, I'm sorry, a perfect root in the denominator so that it can just become a regular number. We can get rid of the radical. Okay, so here I'm looking at my 5th root, and 2 to the 5th power is 32. So if I can make the denominator a 32 and I take the 5th root of it, it becomes 2. So if I multiply, should be multiplied, if I multiply this by 4, okay, the 5th root of 4 on the top and on the bottom, then I get the 5th root of 28 on top, and I get the 5th root of 32 on the bottom, all right? And the 5th root of 32 is 2. So the answer to this one is 5th root of 28 over 2. 32 is a popular number when you're talking about 5th roots because it's small. Once we get into, 3 to the 5th power, then we get into bigger numbers. So they use 32 a lot. Okay, now another situation that we could have if there is a plus or a minus in the denominator that includes a radical, why couldn't I think of that? A radical, okay? Okay, the way that we get rid of that is we multiply it by its conjugate. Okay, so if you want to pause and read this, that's fine, but I'm going to show you. So let's say we have 1 over 5 plus the square root of 3. This is not its simplest form because we have a radical in the denominator. But we also have a plus here, so I can't just multiply it square root of 3 over the square root of 3. But when I multiply it by its conjugate, 5 minus the square root of 3, I have this situation. A plus b times a minus b equals a squared minus b squared. And this is nice because when I square this, the radical goes away. So when I multiply the top, I have 5 minus the square root of 3. And on the bottom, I have 5 squared, 25, minus the square root of 3 squared, which is 3. So I have 5 minus the square root of 3 over 22 is the answer to that one. Okay, so I have some that I want you to try. And so go ahead and, well, I'm going to actually do these in the next video. So you can just look at these and I will give you the answers in the next video.